continue with the next speaker, who was again a PhD student here at IBS, Yeongjun Kim. He will speak about metal-insulator transitions in weakly disordered flatbands.
Okay, thanks for the introduction. Hello, everybody. Today I'm going to be talking about the metal-insulator transition in infinitesimally disordered flatband. I'm a student of the UST in Korea, and I'm also a member of the PCS IBS. Okay, on Wednesday, Tilen gave us a very nice and detailed talk about this subject. The main result is that in the flatband whose all of the bands are flat, the metal-insulator transition can be driven in 3 dimensions in presence of the infinitesimally weak disorder. After the submission of this paper, we are still continuing this project, and about this ongoing project, I will give a brief explanation, although it's not conclusive yet. So our work is about the all-band flat lattice. The figure on the left is one example of the all-band flat lattice, and this all-band flat lattice has a band structure whose all bands are flat. And we are interested in the effect of the disorder in such systems in any dimensions. However, we don't want to confine our interest to some specific all-band flat model, but a general all-band flat lattice we call manifold. So for this purpose, we first systemically construct the all-band flat lattice, starting from the translationally symmetric diagonal Hamiltonian, which is trivially all-band flat. We apply a series of the 2x2 local unitary transformation to each of the unit cells enclosed by the blue shade in the figure. Since the unitary transformation do not alter the spectrum, in the end of the transformation, we have the general formula for the all-band flat Hamiltonian with nearest neighbor hoppings parametrized by the angle theta. This is the system we study. So if all-band flat lattices are perturbed by the disorder weak compared to the band gap, each flatband energy is broadened in a disordered way. But since the disorder strength is small, the perturbed energies originated from one flatband are still far from the other flatbands. Therefore, in the weak disorder regime, we can project out all the other flatbands except one we study, and we can simplify our problem. It turns out that after you project, the disorder strength W simply becomes the scaling factor of the Hamiltonian. As a result, no matter how small the W was, the scale-free disorder part is always of order of 1. Therefore, the weak disorder immediately entangles all CLSs with disordered hoppings of order 1 and destroys the CLS. And this results in a non-perturbative evolution of the eigenstates. But how about the disorders other than diagonal? Or even more, how about the mixing of the different types of disorders? Specifically, we are interested in the 2 different types of disorder. So in the type binding network, we have the hopping element, and this one type of the disorder we consider next is the hopping disorder, and this represents the disorder in the strength of this hopping. And the second type of the disorder is called the phase disorder. So what is the meaning of the phase disorder? First, if there is a magnetic field, magnetic flux transfers to the lattice, we can show that the hopping becomes complex, and this is known as the Pyer substitution. So the phase disorder represents the random magnetic flux of the system. The motivation for this studying this new type of the disorder is that we wanted to see if in the all-band flat lattice, whether the metal-insulator transition can be driven in lower than 3D, specifically in 2D. The other motivation is actually the experimental point of view. Since we are dealing with the infinitesimal disorder, these types of other disorders should be always present in reality. So I will now only focus on the 2D all-band flat lattice. For the numerical study, we adopted the multifactor analysis. What we are seeing here is called the tau and the q, which can be obtained from the wave function after exact diagonalization. This quantity represents the scaling of the qth moment of the PDF of the wave function squared. This can be understood as the scaling of generalized participation ratio, where the exponent 4 is simply replaced by the 2q. The black solid line represents the ideal metallic behavior, where the wave function amplitude scales uniformly with the system size, and the dashed line represents the localized state where nothing scales. Between these lies the multifactor states. If the wave is in between these two lines, the wave function have the continuous distribution of the fractional dimensions. Hence the name the multifactor is given. It is well known that at the critical point of the Anderson transition, the eigenstate shows the multifractality. We conduct the multifactor analysis for the eigenstates close to the band center. For the diagonal disorder case in 2D, which is shown in the figure, we can see that the tau is moving towards the localized lines, and it is indeed localized in the thermodynamic limit. Next, we consider the pure phase disorder case. It is not clearly seen, but what we see is that the tau is slowly approaching to the metallic line monotonically. To see this more clearly, I show you the tau at the vector q equals 2. And it is indeed monotonically and slowly increasing with the system size. So we may conclude that this is a metallic state, but I will not draw the conclusion that this is a complete evidence of the metallic state. But based on this, this result, at least for the system size of up to 140, and if our analysis is correct, then it is approaching to the metallic state without the hint of the diminishing. Next, we consider the pure hopping disorder case, and the result shows that the trend was completely random, and from this result, we might conclude that this is a multifactor states. So the conclusion is the following. So urban flat lattices are systemically constructed, and the scale-free Hamiltonian is derived under weak disorder regime. In our presentation, we only focused on the 2D urban flat, and 3 different types of the disorders are considered. Numerical results might indicate that pure phase disorder might induce the Metal-insulator transition. And to resolve this more clearly, careful analysis and simulation on the larger system size needs to be done. So there are still lots of interesting things to be done. And this is the end of the presentation. Thanks for listening. Thank you.
So, thank you for this nice talk. Yes. So are there questions? Any questions? So this doesn't seem to be the case, so.
Okay.
So it was, yeah. Okay, so then we can continue. Thank you again for this nice talk. It was very informative, and